Hello and welcome everyone. Apologies for the slight delay. We've just been experiencing in classic style some technical difficulties, but thank you for bearing with us. Welcome to part 2 of our introduction to C++ and to our second in our 4-part coding workshop series for the student community. Thank you so much for joining us. My name's Julian. I'm not going to be chairing the session. I'm just standing in for Deandra while she joins. But I'm the Student Engagement Officer at the IOP, and I'm delighted to be joined again by the team of students and campus ambassadors who put this session and these workshops together during the winter months. So I'm delighted to be joined by Chloe at Wolverhampton. Hey, Chloe. By Nikki in Trinity College Dublin, although I'm not sure you can see Nikki on screen, but I'm sure he's waving. We're also joined by our, who else is on the team here? Beg your pardon. Surya will be handling the Q&A later, and of course, Rohit Goswami, who is today's wonderful presenter, a doctoral researcher at the University of Iceland, Reykjavik. Thank you so much for delivering this session today to our attendees. Participation in the workshop shouldn't require any pre-installed software, and everything demonstrated will be available for students to edit and run online. I'm going to hand over to Surya now for the housekeeping, and then we'll kick off with Rohit's fantastic presentation.
All right, thanks, Julian. Hi, everyone. Hope everyone's doing good today. As you can see, you've all joined as listener-only mode, but you can contribute your thoughts and your questions to the organizers in the question box, and we'll read them out and share them to Rohit at intervals where he can answer them. Alongside comments, please do ask questions for our group discussion and our Q&A, which we'll be doing in about 45 minutes following the presentation. And we'll be constantly monitoring the chats and answer any questions where appropriate. Also, you can access the slides from the control panel under the handouts. And Chloe will be posting hyperlinks for each section of the code as we go along, so you can all keep pace with practice. Additionally, a recording of the session and slides will be circulated afterwards, so do keep an eye out for that. Also, please note that by attending this webinar, you're agreeing to the IOP Code of Conduct, which can be found on the website. Okay, back to Julian.
Wonderful, yes. So just a reminder, the next sessions in the series are on Saturday the 17th from 1 to 2, and that's on Julia. And then we have our Introduction to R on Monday the 19th from 5 to 6 p.m. Let's get things started. For those who've just joined, thank you so much for attending our second workshop on the wonders of C++. If all the other panelists could now turn off their webcams, mute the microphones, we'll leave you in the very capable hands of Rohit Goswami from the University of Iceland in Reykjavik.
Thanks so much. So is my screen visible? Not yet.
Just making you presenter. Give us a sec. Should be popping up on screen now.
Yeah. Okay.
Perfect.
So is everything visible?
Yep. Looking good.
Fantastic. Okay. I'm really happy to be here. There's not a lot of time and there's a lot of C++. It's a very old language. So let's get right into it. So that being said, more about me can be found here, and all of the links on the slides are clickable. So yeah. All right. So, oh yes, funding from RANIS, and very happy to be here from the Institute of Physics, and the slides are licensed under the CC4 by NC4. Okay. So all the contents are on a Git repository, and given the time constraints and a lot of the things that you'll be doing have to do with project management, so every slide comes with a commit ID. I'll point to these, and they will allow you to go to the state of the project at that point in time, which is really useful and one of the best uses of Git, actually. There's also a GitHub discussions. I won't click the link right now, but you will need a GitHub account to access that. So, okay, so let's get right into it. This is the first commit ID. I'll show you what that means. So in the beginning, when you start a project, then the first thing which you need is a README, which should describe your motivation, rationale, licensing, install instructions. In older projects, there used to be a separate file called install, but that's gone out of, it's not in style anymore. The license is typically written in plain text. It's written in plain text so that things like GitHub can parse it and keep track of all of these things. There are shell tools which I would suggest using rather than manually typing out long legalese. Similarly, the git ignore file is really, really useful because it lists what sort of files you want to be committed, what sort of files you don't want to commit, typically large binary blobs, PDFs, or say molecular dynamics trajectories and other such things. Once again, there are tools for this. I personally prefer Gibo. So that's one of the first things to know, that like, sure, the git ignore file can be populated by hand, but it really shouldn't. And that's really going to be one of the main motivating things that we see throughout this talk, that like there is the slow way and there is the smarter way to do things. So on the right is just an example of how you would start a standard project using Gibo. This would then populate the git ignore file with all the files which are generated. So if you've used a Mac, then maybe you've seen .ds_store gets generated a lot, which is completely useless, and there is no need to keep under version control. So these are all automatically inserted into the git ignore file, and licenses can also be generated similarly. At this stage, this is your project structure. Now, I'm just going to open the first of these to give an explanation of what this looks like. It takes you to a commit. And if you go to browse files, so there are, of course, all the changes, but more importantly, this is the exact state which we're discussing in that slide. It's also useful in the sense that you'll be able to see exactly what changes are made here. And the only other thing to say about this is do be careful to right click and open in a new tab or command click, because otherwise it'll open in the same tab, right? Okay, so that's for any project. What about a C++ project? What changes? Well, you probably want to have, at the very least, a folder with your sources, right? And we'll discuss the difference between libraries and executables a little while later in the talk, but yeah. There should be an include because C++ separates source files and header files. Within the include, you will typically want to have your internal project includes and also your external ones, because there are a lot of header-only libraries that you might want to include here. There is documentation. Unfortunately, we're not going to look too deeply into documentation right now, but for reference, right now, the project folder contains docs, which only contains the source of this presentation, but that's still useful. So definitely have a docs folder, even if it's blank, just to remind you that it should be populated. The CMake list file is part of the CMake build system. We'll be talking about that quite a lot. And then finally, there should be, or there can be, depending on how you're doing things, a folder which lists sort of automated installs. The automation comes from the fact that they're meant to be run on virtual machines like remote servers. And so they're not really meant to be installed so much as just to automate certain tasks like downloading some files and storing them. But yeah, we'll discuss CI a little while later. Okay, now the second thing we want to talk about is how source codes get parsed. Now, this is not true of Python, but it is true of most compiled languages. There is a step where, in some sense, we write one style of code, right? We write some syntax, and then it magically becomes machine code and gets executed. The computers only understand zeros and ones. So in the middle, there's a whole chain in these compilers. It's the lexer, parser, but those are all terminology. Now, traditionally, there is a preprocessor which technically doesn't create machine code. Here, there's a popular example which is not C++. It is the SAS to CSS preprocessor. For our intents and purposes, the preprocessor is a black box, and it takes some random file and it outputs some other file. Now, why did we even want to discuss that? Well, it's the way these macros get expanded. So the macros are expanded, like when you type include IOStream, then that is going to be expanded by the preprocessor. What does that mean? It means, well, in this case, whatever is in the IO stream file is going to be inserted directly into the program stream, right? Okay, now the question is then, where is this coming from? Now, the angle brackets mean that it's going to be either passed to the compiler with the I flag, or it's going to be defined in the environment variables through an include directive. Okay. Now, if you don't use angle brackets, if you use this syntax, and we'll see in project structures how this changes, then this is typically done for local files. This nowadays is less used because the build system takes care of keeping track of the includes and I flags. So you can typically get by in a standard project, if you've set it up correctly, by just using angle brackets. As such, there's no problem. Whichever one you use, you get to the same thing, but it's something to keep in mind. Okay, so what is the first refactoring which we'll do from yesterday's code? So the first thing we're going to do is we're going to actually make a CMake file with comments. Now, we'd like to segregate the build. Now, why would we like to segregate the build? Well, once we've compiled the code, we'd like to also get a clean build, right? And that's hard when you're building in the same folder. Then there are all these object files that you need to remember to delete, and that's just not good. So instead, we will make sure that the build system will not allow you to try to make the binary in the source code folder, right? That's the first thing which we'd like to do. And how are we going to enforce this? Well, we enforce this on the right is the code which goes into the CMake file. We start by adding a nice little comment about, so we say we require at least 3.14 or it's going to error out. This is a very human readable syntax, the CMake syntax really. We could have also defined multiple languages here, but we will see that we don't need to for this project. The important thing here is the include guard, which says that basically if the project source is the same as the project binary, then die, give an error and fail. And in fact, give this message. Now, what does work is making a separate folder and then doing this. Now, this is great because then every time you want to change something, suppose you want to switch compilers, you can just delete the folder, change your variables, and remake this entire process. It's all cleaner in some sense. Okay. Now, what about header-only includes? Header-only includes are meant for small classes which have inline definitions. We'll talk a little bit more about what the difference between a definition and a declaration is later. But for now, if your code is very small and very short, then it's a good use case for inlining a definition. Okay, these are header guards. They are part and parcel. By the way, when I say header, I mean both .hpp files and .h files. So if we want to take a quick look at what that means, what are we talking about? What is the actual file we're making? We're talking about making this IOP vector class, this vector header, right? We're making this file, this .hpp. And where is the code coming from? Well, we're stealing the code from yesterday's main, right? Okay, now importantly, these are documentation comments, which we're also sadly not going to discuss right now. We can see that later. Okay, so why is it good to have these header definitions? Remember that this macro, this pound sign, the hash, it expands the entire thing into your code base. So naturally, you don't want to do this multiple times. And the if and def define headers, these header guards prevent multiple inclusion basically. Now, the whole game behind making a good C++ project is about modularity. We'll see this time and time again. We want better guarantees. We want smaller code sets. We want to be able to test each one of these so that we can be reasonably sure where things go wrong, right? Now, the changes made when we start adding a library, when we start adding this HPP file, remember now we don't just have one file, we have, it's not just main, it's also the HPP. Thankfully, the build system takes care of this. We simply define a list of sources and we provide that here. And in the second step, what we're doing is we're saying, remember the include directory. Notice that I use angle brackets here. Okay, yeah, so this is a fun thing. Here we have angle brackets, and if you recall, I mentioned that angle brackets mean that the linker, the compiler, needs to know where to look for this IOP vector. And that's really what we're telling the CMake file to do. We're saying, hey, include this directory, our own project's include directory, right? Okay. I personally prefer the angle brackets, like it's just the way I work generally. Okay, what about namespaces? That's for even better modularity, because if you imagine, there might be a situation where you have two files and the same function. Let's say a common function like vector, right? And then how do you know which vector function to use? This is a problem which in Python is often understood in terms of shadowing, like the most local one gets precedence. But in C++, the right approach is to simply use a namespace. Some beginner tutorials often do something like using namespace std or whatever. Don't do that. Never do that, because then later down the line, you don't know which function is coming from which namespace, and it's a huge mess. Larger projects should never do this. So there's nothing special about namespaces. There's nothing special about standard. We are going to define our own. So we make our own namespace, IOP dat, and we put the class particle in there. Okay, the point of a namespace is that it allows different files to share their code. Okay, so even if we now define multiple classes and multiple files, because maybe I want to maintain one, my friend wants to maintain another, she's better at it, so she will maintain her file, but they're in the same namespace. So to the user, when they're running the code, they get this sort of unified access to, they'd just be doing IOP : IOP dat : vector, I mean particle, yeah. So, and in fact, that's exactly what is shown here, that if you have two files, then they will still share the same conceptual region. Now, when you add a namespace, then the compiler very smartly throws a new error, and it's a good error because it says that vector3 no longer exists. There's no object called vector3. There is now IOP dat vector3, which is a pretty smart guess. Maybe you meant that, which is absolutely right. So we add the file, the new header file, and we add the include, and we're done. Now, notice in the previous one, if you're following along, or later if you go backtrack and take a look at the comments, then you will see that we have regrouped the structure of the code. Okay, where previously we were using math types for vector, now we have decided that, well, I'd really like primitive data types to be both vector and particle. Okay, it's because there are a couple of reasons for this. In this particular case, the vector class was not very involved in the first place, so it just felt like a more natural thing. Now, refactoring is very common, and you should refactor. Every time you think maybe it's easier to do it this way, do it. But you should always test, because otherwise things will break and you will not know, and then it's very difficult to work with. Okay, so why are we still discussing libraries? Well, because there's another kind of library. Until now, all our libraries are essentially adding header files and then just sort of including the code in. Now we're going to look at a different kind of header file, well, a different kind of structure. So previously, we're defining all of these within one file. There's a .hpp, and it has the definition of this function in there. But often it's better to have a header file which just contains the definitions, and documentation, brief documentations. We'll see that. So a couple of reasons for this. It's easier for people who work with the code. You open the header file, you know exactly what is expected out of each of these classes. And the definition, 9 times out of 10, maybe you don't even care about the definition. You just want a short, readable header file. Okay, so header-only files are easier to include, of course, because you can simply remember in folder structure, we have include, and then I mentioned you can have internal and external. So you can just drop them in and use the quotation marks to access any of those header files, right? You can drop them in, you can version control them, it's very easy. But it slows down compilation significantly. Every time you compile a header-only library, you have to sort of, as you can imagine, you're reinserting the entire contents of the .hpp, and then you're continuing with that. It's slow during compilation. I maybe should have mentioned that clearer here. Compiled code is faster to compile for sure, because you don't need to recompile things which have not changed, right? If you've compiled the library once, then you're free to use it later as well. Typically, compiled code will require you to use a build system. And one of the takeaways from this workshop should be that it's not a big deal. A build system is not scary at all, but it is more or less required. Otherwise, it's kind of tough. So, but the separation of header and source is always more readable, right? I mean, we saw that in the last slide, that we were able to see the entire contents of the time stepper class, or at least what it's expected to do, right? So what does it look like now when we've done this? Well, at this stage, what we're looking at is we have our include and we have the data types. I've not expanded that because we know what's there. They're two files. What has changed is there's a physprocs.hpp, and now there's a corresponding source file with it, physprocs.cpp. Okay, so how do we do this really? You declare things, and now here we can see the syntax in a more full way because I'm also including the comments and what sort of comments you should have in the header and in the compiled code. So we're going to take this sample of the step function in time step. The build system here, as mentioned in the slide, really takes on most of this debt. Okay, it's going to compile it, it's going to link it, and it's going to manage all of that for you. It's going to give you the executable at the end. That's what it's there to do. Okay, now you define it in the CPP file. Now notice that the way the documentation works, the way Doxygen documentation works, Doxygen is this fantastic documentation system. It is a good practice to give the brief and returns and parameters in the HPP file so that someone who looks at the HPP file will be like, oh, okay, step takes a step, I see, and it returns nothing, which is useful to know. And the details of how this works should really come in the CPP file. There you say detail, the algorithm, does this, does that. You should also have individual comments, which I've deleted in this case, which describe each step. So sort of like the algorithm steps, and this documents the overall structure, right? Okay, how exactly, like where's the code, where's the comment? Well, first of all, this is the comment, and let's discuss it. There's also a mention here about how you can actually build header-only libraries as well, because there's no monopoly on just building compile libraries, but we don't care about that right now. Okay, it is fairly simple, but there are a few things to note here. For one thing, we now define an additional target. We say we're also building, so we're not just building, oh, sorry. Okay, that should not have happened. Okay, yes, sorry. So we're not just building simulation.exe anymore. We're saying that we're building simulation.exe, but also this library called IOP lib. And IOP lib, okay, CMake is smart enough that it automatically finds headers in the include directories, okay? So here we say, we just include the CPP and we say that this is a shared library. And then we say we need to include all of these files, which include physprocs.hpp. They're all in the include folder. Then we're going to define the fact that simulation.exe needs this at runtime. It has to be there. So we say that it must be linked to IOP lib, otherwise it's not going to run. And finally, we define the order. Here, the order is trivial, where there's only one library and only one executable, but oftentimes there are cases, and in larger code bases, where you have multiple libraries, and then their ordering does matter because of shadowing and other, the dependency tree does matter. Okay, when should you do this? Well, as I mentioned, larger projects refactor often. Modularity, it's a good idea for each code bit to be maintained by one person, right? Someone needs to take responsibility, and it becomes easier to reuse. If I only want one function or one class from a library, then if it's in one separate file and it's part of a library, I can just take it and use it in my code, right? The speed benefits in, oh, okay, I did specify, in compilation time is considerable, really. Examples, Boost is mostly compiled. You'll see a lot of hate for Boost, especially when people try to compile it on their own. They can't find it in their system. All of this is mostly because people don't use build systems. They try to use GCC, and in that case, you need to pass all the flags manually. Your I include files, your L linking flags, all of these, the build system should take care of it for you, and it does very easily. Eigen 3 is famously header only. I have worked on projects where there are multiple different parts of it using multiple different versions of Eigen, because just yeah, it was a nightmare because they had like one version of eigen in some subfolder and another version of eigen in another subfolder. Why? Because the header only include. It's terrible. But I say in general, libraries are fantastic, you know, as many as possible. Let there be more libraries so that we can interoperate our code better, right? Okay, are there any questions at this stage before we move on to the next part?
Hi there. Yeah, no, I don't see any as of yet. So I think the best thing is to just let you keep going and let them pile up towards the end so we can get through your information. It's really clear and really good. I'm scribbling away here.
Cool.
Sorry, one did just pop in the question bar. Matthew's asked, what's the difference between C++, C, and C hash?
Okay. The truth is they're extremely different and they only share a name. Like, so C hash is, it's one of the object-oriented C. It's closer to Java than to C, really. I mean, so if you were to look at C as the sort of base library, base language, and say, okay, C++ looks like C with classes, but C hash looks like C with classes if it was meant to mimic Java. So, like, yeah. The hash, I mean, it's a bit of an unfortunate naming. So I know some people who work on Q#, which is this quantum computing language, which also has nothing to do with either C hash or C++ or anything. It's an unfortunate naming tick, which seems to show up a lot in programming languages. Sorry about that. Okay, so moving on to package management. How do you actually manage packages? Like we mentioned Boost, we mentioned Eigen3. How does this work really? And first of all, let's talk about, I'm gonna ignore this. Okay, let's talk about Python. There's this famous XKCD comic, which is about how easy it is to get strangers' code into your system if you're using Python. Because there are multiple reasons for this. First of all, Python is a latecomer, right? I mean, Python came late and people realized that, hey, we have the internet now. Remember, when C++ was first conceived of, there wasn't really much of a net. There was no concept of having this sort of the PyPy registry, right? The PyPy registry allows you to download arbitrary amounts of code which people have published online. There's the pip packaging manager. There's nothing like that in C++. I love the comic. I'm not going to read it out, but I expect everyone to be reading it. It's hilarious. And the truth is, you know, especially in Python, which is not strongly typed, it's impossible to know what the code does. I think Python is terrible for large-scale projects. You know, when I shudder really, because you never know what is. There are no guarantees. You know, in C we have strong guarantees. We know. Okay, I typically plug Nix, but we're not getting into that. It is a functional programming language, and it's great. It's for declarative packaging. Not now. Instead, let's talk about how we do this in C++. Over the years, there have been many approaches. There's Conan, there's Visual Studio packaging. There are a whole bunch of them. We are going to focus on the newest one, one of the newer ones, called CPM. There are actually two CPM projects, but one of them has not been in development for a while now. So, okay. Now, the other thing is, what if you just copied someone's system over? You want a different GCC? What if I just go back to Ubuntu 3 or something? You know, that's a good way to get GCC to state of the art then. And that's really the concept which these lower guys, these virtualization environments try to get at. You know, Docker especially is, their idea is, hey, you want an older system? Let's just boot a whole new older system and give it to you. Pros and cons are there. Let's not get into that too much. There's also all of these other systems, but yeah. For our use case, we care about CMake, our build system in our project, and CPM, a new style of package management, right? Couple of things about CPM. It is really simple to get, and it is something which they expect you to commit. So you would keep it under version control. Typically, okay, this is part, so it didn't show up earlier in the folder structure, but a CMake folder is common to a lot of large projects because it allows you to sort of define little functions of CMake and dump them there. So CPM is distributed in that manner. It does tend to rebuild things, so it's a good idea to export this command. And then the inclusion is extremely simple. They have a package log, but it's currently not in great shape, so I actually don't use it in the code, even though I mention it here. But okay, why did we even do this? Like, Cool. So now we can add libraries. What are there libraries we care about? I mean, we mentioned Boost, but everybody does apt install Boost, right? What's the problem? Well, there are many problems, but yeah. Let's talk instead about testing and continuous integration. First and foremost, C++ does not come with a testing framework. None at all. Secondly, C++ has the best testing framework infrastructure around. It really is very good. There's Catch2, Google Test, Doc Test, which apparently is new and very fast, but I've not used it. I prefer Catch2 because it's header only, and when I was learning, I didn't use a build system. So what are tests and how do you do them? So the first layer of defense against users saying your code is wrong is the unit test. The unit test is very annoying to write. When you start writing code, you're like, why would I test that 2 + 2 is 3 or 4 or whatever in my context? The reason why you write a unit test is not that the result is obvious. The reason is later the result might not be obvious. It guarantees that at least at some level you know what the code is doing. If you're doing a Fibonacci function, at least you want to test that, you know, the 0th one is 1, etc. If you're doing a factorial, my bad. So these sort of things are what you put in unit tests. Integration tests are for workflows. You have perhaps a molecular dynamics simulation and you're testing the radial distribution function. And you want to see that the radial distribution function for ice looks like this, something, you know, there's a double peak, whatever. That's an integration test. There are many functions that go into that and only one result, right? Adding this, and now here is our first use case. First of all, CMake has the beautiful ctest binary, which is built, and we'll see that in a little while. We add a new directory called tests, and within tests, we add a new CMake list. Here, we finally use CPM, which we saw a few slides ago, right? So CPM is really simple to use. You can just add this catch thing. Now, there is a catch, sorry about that, and that is when you define it, and it has to be defined, where is that? Yes, here. So, and it's actually not very difficult really. So you can link it as, once you've added it as a package here, you no longer need to do find package, in case any of you are familiar with that. Oftentimes in older code, you'll see a find package directive, but CPM add package does that internally. Now, I want it to be very clear that the test binary is a new executable, which is defined here. It has its own main and it has its own 2 tests. We'll see that in a few seconds later. Okay, compile features. Catch has some special features if you have C++ 17 onwards, so I linked them. We don't actually use them though. So adding the test is very nice and simple. We can define what the file is, what is supposed to be run, and this is just a nicer way to name your tests in case you were feeling annoyed and you wrote something you shouldn't have. You can rename it. Okay, let's actually write a test. What is the main file? Well, the main file, this is only to be done once. Typically, anything with a macro is something which does not need to be done multiple times. So you must not repeat this catch config main macro, because remember, macros expand. If you have multiple of these, then you have multiple catch mains. That's terrible. There are many examples. The official documentation is fantastic. There's also a bug in the code, which I left in there, and feel free to take a look at it and, you know, make a change and really add that in. This comment showed how you can move all those mains which you were testing yesterday into their own little tests, which is the better way. I mean, well, it is the more modular and easier to work automated way of doing things. Okay, so if you want to test a vector class, what does that look like? Well, first of all, this include is important. Well, they're all important, but this tells you, this basically defines test case. Otherwise, that would give an error. The rest of these are your standard code macros. These are part of your code and nowhere else, right? And we say, okay, we're testing the vector class. What is it that we're testing? This is actually a funny thing. The vector class, if you recall, is defined in terms of doubles. And here you can see that this basically is just testing that the size of these are right. So there are 3 elements, but there are 3 doubles. So because of that, you know, you need to divide by the size of a double to actually get the number of elements. And we only defined a few operations, including the bitwise component-wise addition, and we test that here. Okay. Now, continuous integration. Why and where and what is it? Well, back in the old days, if you had a computer and I had a computer, then one of the most common arguments is it works on my machine. And this "it works on my machine" is the world's worst error report, because God only knows what's there on your machine, right? At the same time, it is true that different operating systems have different characteristics. Macs are different, Windows are different, Linux distributions, there are as many of them as there are stars in the sky. There are too many, right? And also some tests, especially integration tests, can run forever. Like Nix packages takes over a day. I never run those locally. I submit a pull request and pray that I got it right. Well, yeah, so basically the continuous integration services, they run your code for you in the cloud. I have crossed out Travis because of their new and horrible approach towards open source. I personally have over 80 open source projects. They were like, please give us, submit in writing a reason and a proof of license. And I was like, I don't have time. GitHub Actions is what we're going to talk about. It is great, and it's also really easy to set up. Under the hood, most of these are spinning up Docker systems for you. It's just something to know in case you have errors and you're not really sure why they're coming. They are, and we'll see that in a few seconds. Okay, GitHub Actions. What are they? How are they? What are we going to do with them? Okay, first of all, I like GitHub Actions the most because GitHub Actions has Act. And Act is a command line program which allows you to locally test your Actions workflow. This is fantastic. Of course, it does generate a Docker image on your system, and it's kind of slow and it freezes your computer, but at least you can debug exactly what's going on there. Okay, what does it look like? Well, actions are defined in YAML files. Most things are defined in YAML files. Configurations, it's very popular nowadays. Only Python uses TOML. We don't need to talk about that. And the most interesting thing about this really is the matrix. Okay, this is something which doesn't get covered a lot in the documentation either. And the matrix, where you say where it runs on, is really the most powerful thing. You can then say that, like, okay, it's going to run on an Ubuntu machine. I want it to run on a Mac, and I also want it to run on Windows. By the way, the code which we've written does not run natively on Windows. It does run on Windows subsystem for Linux. We can talk about that later. Now, the steps are pretty much exactly what we do on the terminal, so there's no need for us to discuss it. This, however, is an example of where ctest shows up. So when we compiled the previous code, right, when we wrote the test, and if we were compiling this as we went along, then we'd run ctest in the build directory, and yeah, that's basically what's being said here. Okay, now, finally, before we move to the last part of our talk, embedding and mixed compilation, are there any questions right now? Also, how am I doing on time? I don't have a clock around me.
Hi, Rohit. Yeah, so as far as time, we're almost running into the question period. We've got about 2 minutes left. So I was thinking maybe if you want to go to the part where you maybe show them how to put the simulation together with the code, with the slides that we've given in the handout. That might be a great way to round it up for the last 5 minutes.
Okay, cool.
If that's okay with
so
you.
The first question is, oh, sorry. Did someone say something?
No, I think you're okay.
Okay, cool. Right, so the first thing very quickly is, why would we want to embed? Typically, we think maybe visuals, but honestly, if you want to visualize something and you run something on the cluster, then you don't want to also run something on the cluster to visualize it. You'd want to bring that file home. And that's exactly the approach which Joseph talked about yesterday, that you can simply output a file and then do whatever you want to that file later in privacy of your own PC. So why do you even care? Now, there are good reasons to care. Okay, and a good reason to care is that you don't want to recompile your code every single time. So this is an example of a scientific software which uses Lua to expose a scripting engine. It means that the user is able to compile the code once and run things multiple times. Think MATLAB, think PowerPoint. This is the way most GUI systems work. You install once and then you do a whole bunch of operations then. This is another example. Eon is a long time scale dynamics code. It basically, this is a very good example because, so as I mentioned, C++ is old and Python is newer. So Python is better for doing networking operations. So if you're running a server client architecture and you only require limited communication, it makes sense here the server is implemented in Python and the clients are implemented in C++. The clients need to be fast because they're doing minimization in a high dimensional space. They're finding saddle points on the energy surface V. Never mind. Okay. So we're going to talk about PyBind. There are other things, other libraries, CPP, the CPP Pi, which is also very good. But anyway, the first basic example has nothing to do with the code until now. What you do need is to follow the install instructions, right? Install it on your PC. On a Mac, I ended up doing it with Brew for some reason. And then you also need to install the Python module, in this case, Matplotlib, okay? We will manage it with CPM easily, right? So we add the CPM package and we include this. Okay, now here, this is a good use case of a namespace. You know, here we have PyBind and we're saying just the embed part of that, the embedding library, right? Then this is basically a sinusoidal data set. It's a decreasing thing. And this is the important part. This is where you're actually using this. Okay, the guard is important. The guard is, I'm not sure if many of you know this, but Python is not multi-threaded. It runs on a single process. Sorry, it's not multi-core. So the guard basically reserves this one Python process to keep alive. It is, and that needs to be run. So you start that here. Then what all you're doing is you're saying, hey, this is a C++ object. Now put it in this Python variable. And then you can execute arbitrary amounts of Python code there, right? This is just standard Python. Okay, this looks like this. If you were to run it, then you'd get this nice visualization, right? Now, in case of our Proton stepper, it is exactly the same. The only change we need is because time stepper does not expose the particle position, it's a private variable, we required writing some getters. We didn't really need to, we could have done this another way, but this is a good approach. And then we're keeping track of all of these at every step, right? And this is the output. The code, of course, is standard Matplotlib Python. Okay. So just in order to not, cut into the time too much, there are some very major topics we omitted: documentation, package management at the OS level. We discussed it briefly, but not really. HPC and parallelism. How do you do high throughput calculations? How do you do, fast calculations? Code review practices, Scrum, teamwork, their whole courses on this. I actually took one, it was horrifying. Inter-process communication, how do you actually communicate if I have a Python process and a C++ process and I don't want to go through IO? We did not discuss that. What we did discuss is embedding. There's a slight difference there. The embedding is sort of like a master-slave calculation, right? And the inter-process communication is kind of at the same level, two separate processes, right? Okay. Here are some further resources. I would strongly suggest, if you have a good background in C++, to go over the modern C++ tutorial. It is basically all the new features, all the nice syntax from C++ 11 onwards. Then once you've done that, to figure out where the community is going, what they're tending to do, there are the C++ core guidelines, which are maintained by by Bjarne, who's the original author. Visual Studio is surprisingly good for an introduction. If you don't remember any C++, then Visual Studio is actually good. There are even some projects, but these require Visual Studio. So I'm not sure about the projects, but these are pretty good. Next, that's about package management, and this is about documentation. And surprisingly, C-Line's first portion describes quite a bit of unit tests and why they're good and what they're good for and all of that. So that is the end of my presentation. These are the references, and I'm very happy to take questions now. Thank you.
Great. Thank you so much, Rohit. That was an amazing presentation. I feel like we'll learn so much. So I'm just going to quickly make myself presenter here. Let's see how well this is working. Great. Okay, great. Someone on the team can just confirm that everyone can see everything. Yeah, I want to apologize for my Wi-Fi earlier as well. So if I could just all ask the panelists to please switch on their webcams. And please keep posting your questions as you're thinking of them, and we will endeavor to answer them. Yesterday, we went over a little how we're aiming to finish. We went over a little, so we're going to aim to finish on the hour today. But feel free to leave, or you may continue to ask for a couple minutes with any extra questions that you might have. So now I'm going to hand over to Surya, who's going to handle the Q&A.
Yeah, thank you, Deandra. So great talk, Rohit. I was just wondering if you could talk a bit about how you use C++ in your research work and the advantages of using that over any other language.
Okay, right. So I actually, so I'm a computational chemist. So a lot of my work has to do with high performance computing clusters. And the biggest problem with Python is, as I mentioned towards the end, that it can only run on one process at a time. So it doesn't have the ability to work on multiple cores. And that's the very first problem, right? Now, C++ is more modern than Fortran. And so that's why I ended up with C++. But really between C++ and Fortran, it's kind of hard to choose at some points because Fortran does have inbuilt intrinsic libraries for doing a lot of computations. And yeah, so I use C++ mainly for high dimensional optimization problems, for solving the Schrodinger equation, for doing finite element method calculations for I used to be a chemical engineer, so I used to do finite element calculations on heat transfer, mass transfer, big reactor design, etc.
I see. And if I'm not mistaken, they use a lot of Fortran in finite element analysis, right? So, right, I see.
One thing, sorry to interrupt, I'm just going to make you a presenter, Rohit, so that we can see the captions pop up on screen. If you could share that as before, far away. Sorry.
Right. And also, we've had a few questions from yesterday, which I think would be interesting to hear from you from. So what's your general workflow like when you're doing your programming? For instance, what ID do you use, or what tools and softwares you use?
So I think one of the main things which I use, and I think that may have been clearer here as well, is that I always keep a Git log, and the Git log basically tells me exactly what I was doing at all times. And I can't recommend it enough, really. So, and also testing, like one of the first things which I do is I set up this sort of scaffold with the build system, and the IDE, I personally tend to use Emacs, but there's no real reason why any other IDE couldn't do this. The point are these components of the system, right? And what are those components? Components are, there need to be tests run at every step. You need to write those tests, and you need to have a framework which makes it easy to do that. And then you want the test to run automatically because who has the time, right? So, and I think once these aspects are come together, then this is sort of like my go-to structure. And I typically make a library and an executable because I tend to then use the library to make Python bindings and other things with it. So,
I see. And also during the talk, you mentioned you've worked on several open source projects. So how did you get into them, and how would you suggest someone who's new to C++ or any language to get experience in such things?
well, let's see. So I actually started out hacking on Android kernels, which were in C++. They still are, I'm sure. And then at that time, we used to mail, they still had like these mailing lists and all that. But nowadays, I mean, I think GitHub is really just fantastic. The only thing I would say about joining open source and contributing is you have to really care about what you're contributing to. Like, because otherwise, what's really needed to be good at open source and is to think about the problem deeply. If you're spending 5 hours thinking about what is the best way of solving a problem, then that's your contribution right there. And then when it comes to syntax and other things, you can look it up, or the maintainers will help you. Most projects nowadays have a good workflow where you submit a pull request, and you know, the continuous integration takes care of testing whether your code is formatted right and all of these things. So really, the only thing which you need to do is find a project you're passionate about and use it. And that's the best way to get in, really.
Right, great. And another thing from your presentation, so you say there's a very large code base in many of these libraries. So how do the developers handle certain updates to a programming language or such, which might cause their library to not function in the way they expect it? How do people go around that?
Right. So I did mention also, this is a very important question. And the truth is, many code bases traditionally don't do this. Eon, for example, I'm like, yeah. So, which is why as I mentioned, some people actually ship whole header library files which are outdated by like 50 years or something. And that's a very bad practice. And the reason why they do that is because there are no tests. If no one is testing, then they're like, yeah, you know, I had a student who implemented this 30 years ago and he's gone. And I don't know what's going to change and I don't know what was going on. If there were tests, then when you change the library, right, then all your tests will fail, but at least you know why they're failing. I mean, you'll be able to see, oh, okay, I see. So they changed the name of this function, you know, so because without testing, it's nigh impossible. So I would say, you know, and there's been a strong push for this. In Google Summer of Code this time, most organizations are asking for people who will do traditionally maintenance tasks, documentation and like adding tests, these sort of things, which some people think is not really programming, but they'd be wrong really, because that's how programs last.
Right. Yep. And we've also got a question of when you were first learning C++ or any programming language, what did you find most difficult while learning it?
I think the most difficult thing is the fact that the C++ current ISO standard is around 2,000 pages, and it is 6 times larger than the corresponding Fortran standard. Most people never use even 10% of it. And that's both a good and a bad thing. Like C++ is a language where almost anything is possible and everything has been thought of or is being discussed. I think the best way to get into C++ is to look at the standard library and start implementing small projects. Again, you know, ones which you want to work with. If like there's a lot of theory, and equally a lot of that theory doesn't translate into practice. If you go too deep into algorithms and data structures, then you quickly realize that it's kind of pointless. There's no need to rediscover the most efficient way of iterating over a list. That's why the standard range, you know. So yeah, I think that trade-off that you just need to start working with the standard library and start implementing real-world projects was something which I had difficulty understanding in the beginning, because I thought, no, I need to read everything and try and sort of understand the reasoning behind it and so on and so forth.
I see. So just going off that, how important is the version of C++ you use? Could you use a lower version if you're not using any of the advances from the later versions?
I would suggest not. So C++ has changed a whole lot, you know. I mean, it's very far from just C with classes nowadays, which is why this was the first link which I put out there. I would strongly suggest that everyone should at least give this a read. Also because, so traditionally there are a lot of, the whole data structures which previously were not there, like the whole standard range and standard find, and there are these structures now which implement black and red trees. So if you want to do fast searching, you have heap data structures. All of these things are reproduced in very fragile ways in a lot of commercial codes as well, like especially in computational chemistry side of view. There are a lot of these commercial codes and they've re-implemented poorly a lot of standard library functions. It's best to remember why a language evolves, right? Nobody is just like, hey, there's a new feature, shall we just put in a crappy implementation? No, it's like a lot of people whose whole entire life revolves around finding the most efficient way, update the language. And so that's why I think as a user, it definitely makes sense to be on the edge of the language features, really.
Right. And also a question regarding C++ libraries. So what are the libraries out there for visualization? So Python and MATLAB have pretty strong alternatives. So
actually, there's nothing
what would you
there.
say?
I mean, there is root, and I think Joseph mentioned that as well, a root from CERN, but that's the only one. And the reason behind that is most things in C++ tend to, so there are a lot of file formats. So there's the HDF5 file format, which is meant for storing hierarchical data. And the reason behind this is, honestly, most people and most languages assume that you write out your data to a file and then you visualize it elsewhere. The problems of large-scale visualization were not really something which people ever considered before. Like nowadays, if you're running, say, a fluid mechanics simulation, just visualizing that is going to, you know, beat the hell out of your old laptop. But this was not something which was considered a long time ago. Previously, people would think, how many points do you need to visualize anyway? 10 million, 20 million? Put it in a file. So the answer to that, in short, is no, there are no visualization libraries, but there are a lot of ways of binding to other languages, like with Lua or Python and scripting languages like that. So that's the intended approach, really.
That's great.
Great.
All right, I'm going to have to interrupt right here because great question. And we've had some really great answers. And hopefully anything else that you might need, you guys can find in the handouts. But for now, I just want to thank you guys for joining us. I want to thank Rohit for his presentation. We even had a couple comments from Joseph, yesterday's presenter. So just a few quick things to mention before we go. Let me just switch back to here. Okay. All right. So quickly before we go, I just wanted to show the timetable for the workshops. So we'll look forward to seeing you on either Saturday or Monday or both, hopefully, for Julia and R. And then some upcoming events that we have down the pipeline for students and member-led physics events. They will be, there was also loads available online through the events.iop.org page. One thing that was brought to our attention, if you have registered 4 sessions with your non-IOP registered email address, you may not be recognized by the system and you may get an email from us. If this happens, don't panic or anything, just respond to studentcommunity@iop.org with your IOP membership email address to get the joining link direct. There's no need to re-register. So great. So just remember to check out our updated bookstore, range of physical ebooks, a 30% discount on titles. You can find in the IOP community, the IOP Connect, and think about joining the IOP Computational Physics, a special interest group that is also available. And check out Physics World Focus on Computing 2019 from the back of the catalog. So finally, please to tell us in the survey how it went and what worked well in this workshop, what you found most useful. It will launch a few seconds. And once again, thank you to everybody for coming. Thank you, Rohit, and goodbye. So goodbye, everybody.
Bye.